Hello, everyone. Thank you for coming to our, what are we calling this? A sustainable happy hour. So thank you for coming. Enjoy some drinks and food. But my name is Jason Robinson, and I'm the founder and CEO of Evoco. And our mission is to really, and this is a true mission, to close the loop on unsustainable goods for good. We develop, well, let me start by saying we have a technology platform that uses plant-based chemistry to replace petrochemistry in a wide variety of materials that we use in our everyday lives. Everything you walk on, sleep on, or drive in can utilize this technology. We've used that platform, and aside from the multiple patents that we have with the technology, to really focus today on what we're here to talk about is kind of footwear and like materials. So with the footwear industry, we have a lot of problems that we're going to try to resolve supposedly over the next 5 to 10 years with our net zero targets. But the theme you're going to really be hearing a lot throughout this presentation is we have to go beyond kind of what we're doing today with some significance, okay? So you're going to hear a lot about net zero, you're going to hear a little bit about recycling, but you're going to hear a lot about plants and how plants can replace oil, and plant-based chemistry does the same thing and even sometimes better than petrochemistry. So when we look at the material issue, and we'll focus on footwear, we got 25 billion pairs of shoes made every year, and that number is growing at like a 5% year-over-year growth. A lot of other materials like mattresses, yoga mats are made every year, and they're disposed of fairly significantly. So we think that anywhere between 60 to 80% of shoes made every year end up in landfill within a short cycle, okay? But the big issue is the carbon emitted from these materials. The carbon footprint attached to the materials we're using in footwear today account for brands, about 80% of a brand's carbon emissions. And people think, well, I can turn down the air conditioning in my stores and I'll reduce my LCA, but that's not significant enough. What you have to look at is the materials and the manufacturing of those materials in that supply chain on how that impacts your companies, your brands, overall LCA. So when I say LCA, that's a life cycle analysis. That's measuring, accounting for carbon through a mass balance, okay? We have other issues like reusability, recycling, how much can you actually recycle, what's biodegradable, what's not. That's kind of a hot topic these days to discuss what's biodegradable, what's compostable, what degrades in nature, and how does it create microplastics and all these other things. But we'll talk a little bit about some data that relate to that on the basis of degradation is a process and it works with our material. So there's a variety of materials, and some of this is just basic information for most of you guys, but we got polyurethanes and EVAs that are primarily making up a lot of our footwear components, largely on the foam and the plastic side, so the bottom. And we're using a variety of different components relevant to that. We're also using kind of polyesters and synthetics or leathers or leather replacements on the uppers. But talking really about how we replace the bottom part of the shoe or the inner part of the shoe, the insole, midsole, outsole, that's really today polyurethane, EVA, PEBA. You guys would understand some of these materials giving us lots of bounce and rebound, but actually creating a lot of carbon through that process. So when we talk about circularity, we don't necessarily talk about product circularity. We talk about this thing in Evoco called natural circularity. And that's the idea of circulating carbon naturally like nature intended. So product circularity, you take a product and say it's a plastic bottle and you want to reform that into something else. Well, a lot of that's upcycling, not recycling, and that's turning a plastic bottle into a t-shirt. You can't turn that t-shirt back into a plastic bottle, so that's upcycling. And that's not really circular in a product. But what you can do is take that plastic bottle and turn it to another plastic bottle and turn another plastic bottle. That's a little bit product circularity. We focus on carbon and a carbon balance, not just in a life cycle, but actually looking at how carbon was used in nature. So think about how a plant is grown, it's grown over a lifetime, and then it degrades naturally in the environment, and that carbon has a natural circular element to it. Along that life cycle, that plant is actually absorbing carbon from the atmosphere as well, right? Photosynthesis and all that stuff. That's kind of grade 8 science, I think. I don't know, something like that. But what we look at is replacing, in this natural circularity thing, is replacing oil with plants. So that's naturally renewable, naturally low carbon in approaching the material value chain, okay? But we also look at a performance measurement, and this is crucial when we look at sustainability. And we use a kind of a mantra inside Evoco called enduring performance. We like to make things to last, which is not always great when you're trying to sell lots of stuff. But when we're looking at how we approach materials today, a lot of these materials are not lasting, right? You use them for a short period of time and you discard them. Other concepts around fast fashion we won't talk too much about, but really about, the change in colors for a season and all that kind of stuff. But what I want to talk about here is really performance-based. So we really designed the platform chemistry, plant-based platform chemistry, to perform as good or even better than some of the products you're using today and materials you're using today. And at the end of that life, we have to talk about the end of life because it's a really strong part of that, not only your carbon footprint, your LCA, but it actually is a huge element to this waste issue. Think about all the stuff that's going to landfill today. It's creating methane gases. That's largely food waste. The rest of it's turning into microplastics or leaching out toxins into our water systems. It's no joke, and I'm not trying to fearmonger here, but that's the reality of our situation. So if we're looking at the end of life, we want to mitigate the impact on the environment. And you can do that in multiple ways. You can recycle a little bit. You can reduce your waste that way. But you can also look at biodegradation or natural degradation that doesn't negatively impact the environment. So today we have a product called Fates. It's a plant-based eco-foam that is 70 to 80%. Actually, we have a product that's 82% if we want to get that exact. Done by mass, not volume. Third-party certified through USDA, Green Circle. It's also vegan certified, so we're not using any animal product that may come up as new carbon from your C14 analysis, so it's for vegan certified, just to kind of take that information out of the, because some people are using animal oils to convert into chemistry that is being put in some of these materials that we're calling bio today. But this is a high performance alternative and has a significant impact on your carbon footprint and the environment. So when we look at Fates, we designed it so we can use kind of endless product applications. A foam can be used in your shoe, for your insole, your midsole, even your outsole application. But we can also turn this technology into a thermoplastic, into a thermoset, whether it's open cell, closed cell, microcellular. We can derive that technology for a multitude of applications. And that applies now to not only footwear, but when you think about a yoga mat, which we're looking at, which we actually are doing, and things like mattresses and pillows, and then obviously getting into the automotive sector, which is really a quagmire over there. So we're not going to talk about that too much. But how we innovate. So really, the sun of today makes a plant of today, and then we turn that plant into a chemistry, whether it's a monomer, a biochemical intermediate, a biochemical monomer, or a polymer, or natural polymers. We utilize a variety of different technologies and a variety of different feedstocks. We're not focused on one technology, one monomer, or one specific feedstock. So we can use everything from industrial corn, and it's not goes into the food chain to make our tacos or our tortilla chips or anything like that, so don't worry about that. But what it does do is it's an industrial product, and we have some information about land use and how it's not impacting that. And that's a little bit more misinformation in the environment today about the use of corn and the impact on land use and the environment. But we also use things like castor oil and bio waste, food waste, and also some pulp and paper derivatives like lignin and rosins. This is all part of our IP estate, so we don't focus on one product or one material, but be able to derive those materials into a variety of different ways so we can add performance metrics or bio content, reduce your LCA depending on the application. So Fates can go into a variety of different products, and then that product can biodegrade at the end of its life, okay? So how do we start with footwear? Well, about 7 years ago, I was at a trade show with my colleague, and we're looking at, and there were some little bit of recycled t-shirts and a little bit of thing. And I said, we can do better than this. We can make chemistry from plants. And he's like, you're crazy. And we walked around for like 4 hours. I think it was ISPO, looking at all the materials. And so we derived this concept that we could do it. So it took me 2 years to create a prototype. Still started in my kitchen table, actually, and then moved into a company called Evoco. And when we looked at this footwear, we started to really dive into the metrics around the life cycle analysis of a footwear product. And it's only after the last couple, 2, maybe 3 years, where this information started becoming more prevalent and in the public domain. But when I was looking at it about 5, 7 years ago, you tried to understand this, and you couldn't really understand the true impact of the materials on the environment in terms of CO2, in terms of waste, in terms of toxicity. So we dove deep, created an innovation product like Fates, and we looked at these metrics today, and you got something that, okay, we're using pounds in the US. I'm Canadian, by the way, so apologies if I skip between grams and all that kind of stuff, but 30 pounds of CO2 emissions per running shoe, and it's weighing less than a pound, right? I'm pretty sure it is. It's about 400 grams or 300 grams, depending on how light you're getting it these days, and that is less than a pound. So when you're looking at that, that's 30 times the emissions of the weight of the material that's created through a life cycle analysis of CO2 emissions. And there's 300 million pairs discarded every year in the US. I mean, that's the latest metric that we're seeing. So a lot of waste, a lot of carbon, and we have to understand the impact of these materials. They're not degrading in nature. They're sitting down for thousands of years creating microplastics, and the material, as it degrades, not biodegrades as a product, it leaches out hazardous chemicals into the ecosystem. So when we look at this degradation process and this waste process, we've done a lot of work on what is biodegradable, what is degradable, and how that works in terms of a product, in terms of a current supply chain that can manage this stuff. So the orange line there is a product that we have in the market today based on our status quo technology. And what you basically see there is that as over the first 40 days, there's a linear degradation curve on that. And then it starts to tailor out. It's still degrading, but it degrades slower. And that may be a problem when you present it into a composting where you want some sort of turnover of material for degradation and that sort of thing. So we patented a technology that utilizes a material and a microbe that eats the material from the inside out, but only in composting. So when I'm wearing it in the shoe, it's not biodegrading, it's not degrading, it still has enduring performance. But now we have a more linear degradation curve, both from a biodegradation and a degradation perspective. And the way I talk about degradation and biodegradation, when you look at even compost heaps in your garden or industrial compost heaps or how things degrade in nature, you have microbial activity, which is the biodegradation part, but you also have natural elements like oxygen, water, UV, and mechanical turnover. So when you take your compost heap, you mechanically turn that over to move it around to break down some of the material in that process. And so when you look at degradation, this is not taking that into effect. This is a lab environment, so it's only looking at kind of the microbial breakdown of these products. So there's a lot more in nature that we can do with this product to break it down faster with this patent. So the reason why we'd like to talk about this is that it's an important subject that we need to understand. We don't make claims in the public domain about biodegradation, but we do a lot of work from a technical perspective on that. So our product isn't commercial, it's in the market today. And the technology is really based around the idea of making insoles, midsoles, or as a start. And we've worked with Vans on a product where they kind of, because of the performance of the product, allowed it to become a drop-in midsole. So it actually simplified construction. So you don't need a midsole and an insole. You can use a foot contact, no ground contact product that gives you rebound, low compression set. The material in this is about 5 to 8% compression set, meaning it's got enduring performance, going to last longer, feel the same. Gives you some comfort and rebound, so you give you a little bit of performance out of an athleisure shoe, but also allows it to drop into a rubber outsole and then have a simple construction of stitching a canvas upper onto that. So that's a very low carbon impact product because manufacturing is less, componentry is less, and we're also able to drop in a plant-based insole, midsole product and reduce the carbon element of that. So here's an example of kind of where we're going with this technology. One of the things that we see here is a case study around looking at what we're doing today in recycling. So a lot of people look at recycling in upper, and that would be significant reduction in carbon footprint. When we look at that product there, the actual overall, even though the upper takes a large part of the volume and even sometimes mass of the shoe, you're actually only reducing the carbon footprint by 9% using recycle. Now we think that's less actually, but this is all published data that we're using here, so this is not derived on our own, we're using published data. But the idea behind it is that if we use this insole, midsole combination, we can actually reduce the carbon footprint of the shoe by over 30%. And right there it's showing 29%, but it actually is actually more a lower carbon footprint than that. We use more conservative numbers. And so when we look at this kind of product here, what we're trying to show is that you have to start looking towards your net zero targets of not just beyond recycling. And I think today we're seeing a lot of new technology out there that looks at recycling as a product. But what we're saying is we're not saying don't recycle, we're saying continue to recycle. It's a lot of it pre-consumer waste that you're sweeping up the shop floor and reincorporating it back into your product. And that is a good thing because it reduces waste. But it's actually not going to significantly impact your carbon footprint, or if you're a brand, your net zero targets, which are either 2025 or 2030. So we're working with a company and they want to reduce their material carbon footprint by 70%. And they have certain targets of about 3 kilograms of CO2 equivalent. So our carbon footprint is 3 kilograms of CO2 equivalent, but they projected that out to 2030 as a part of their targets. We can do that today, and our innovation is only getting better, and our sustainability element is only getting better with that. So what we're trying to do here is trying to give the understanding that recycling is a big part of the future of this industry. But if we're going to make a real impact on carbon emissions, we're going to have to move to plant-based chemistry to approach that. And we can do that with the concept of not reducing performance and increasing sustainability of your materials. So this is a little bit about misconception, and we get this question a lot. And this is that idea that, oh, if we're going to use too much plant-based, we're going to increase land use, and that's going to affect grassland and planted trees and stuff like that. Well, this is very much not the case. Biopolymers make up a tiny amount of hectares in terms of drawdown from a variety of whether it's plant-based starches from corn or soy-based or other oil-based products from that. But actually farmland is shrinking in the US by about 3% year over year. So that means there's more grassland being planted every year because of efficiencies in the agricultural process. So when you actually look at the biopolymer aspect, the impact on that is actually quite small relatively, and we're not having any impact on land use relative to not planting trees or reincorporating grasslands into agricultural products. So that's a misnomer in this industry, and I think what we need to do is really target that message to kind of help people understand that we are not going to take over grassland, or we're not going to move Amazon to create the Amazon forest to create plant-based chemistry. That is not the intention, and as agricultural land shrinks and decreases, the biopolymers can work within that existing infrastructure. And actually a lot of the products that we do use as feedstock are actually waste products. Starch is a waste product. It's actually not very efficient for the animals to digest. That actually creates a lot of methane, which is a greenhouse gas emission. And so when you actually remove starch from that, it actually helps the animals digest this stuff better. It's just more extra information for you to kind of digest, I guess. Fates, really, what I want to kind of leave you with is a concept, and we will get Gerald up here afterwards and we can have a conversation, but he'll put up some LCA data for you to kind of just look at where our current LCA is. But basically, what I want to leave you with is you've had 100 years to create a feedstock for all the materials you're using. And that was oil, right? And then over the last 20 years, you kind of perfected that to create very cheap, inefficient products through efficient supply chains. And so what we're saying is our company that's 5 years old, we have an innovation that's commercial and out there today. But we need some time and adoption for you guys or the brands to take up and adopt this technology so we can continue our innovation process. And if you give us, our innovation process is actually a lot faster. So when you think about the adoption from a concept to a commercial product, it was actually a two to 3 year timeline. And so we can do things much faster through the innovation process because of things like investment into ESG sustainability platforms like ours, but also the desire now for brands to start adopting this technology. So as people buy more stuff from us, we will innovate further to create more efficient, sustainable products that allows us to not only look at the carbon footprint we have today of that 3 kilograms of CO2 equivalent, but actually start to look at how we move that further and become more ubiquitous in an industry like the footwear industry or beyond. So I'll leave this idea of step into a sustainable future. I think the idea here is that we need to really move beyond the conversation. We have very stringent net zero targets, and that's going to require significant adoption very quickly in order for us to reach those. And so happy to have conversation or take any questions as Gerald puts up our LCA data. Thank you. Does anybody have any questions?
You've spoken about the chemically recycled materials.
Yeah.
As you talk about circularity, like talking about circularity as a way of circularities. The chemically recycled, the yields that they are already finalized in the development process are up to 95%. So I think it's one of the, if you're looking for new ideas to progress, I think that's the way the real circularity would be taking the material out of the life cycle, put it back again as a valuable raw material, rather than just leave it, as you said, it was not biodegradable but compostable.
Yep.
If you throw something in the landfill, it won't automatically decompose.
Yep.
Add some bacteria and everything. So my reflection for the future would be like true circularity would be like putting again into value whatever you take out of the end of the life cycle of the product.
Yeah, I mean, the way I approach that or the way Evoco approaches that actually, is we really focus on what we can do as a company. Obviously, there's a lot of technologies that we can look at and evaluate relative to how they determine their circularity or their impact. But what we do is measure our impact today. So our impact is a 7 to 10 times reduction in carbon, okay? We actually have a case study where we show an EVA insole is about 2.5 kilograms of CO2 equivalent, and our insoles, based on that weight, is about 0.38. So what we're trying to do there is show you today what we can do is tackle the challenge of trying to get to your net zero targets. That's what we can do for you today. What we're looking at in terms of the circularity element is that we can incorporate natural circularity, product circularity, and recycling into a variety of different platforms. We're not saying don't do that, but the way we approach circularity in our product is through the idea that we can take these products, and I guess maybe I should explain myself better. We don't have to do anything to the product. It just, if you throw it into the landfill, it will just take longer. Landfill's anaerobic, and it's more efficient to degrade things under aerobic conditions. That's why composting is aerobic. So what I was just trying to explain there is that through our patented technology, we can keep that degradation process moving to degrade it at a faster rate so it can be in composting. But the idea that a lot of these things through circularity, a product circularity, taking a shoe take back program, all these things are going to take time to implement, right? And then taking different components out of the shoe and stripping them down So what we can do for you today is, you know what, this stuff is going to end up in landfill. That's the reality of it, right? So you can know internally, externally, that if it does end up in landfill, or by chance in your garden compost, it will degrade and will degrade over time, but it won't affect your performance. But I think we just need to look at things in a more circular way, but in a way that, you know, there's going to be a lot of technologies and a lot of things that we can do to impact. This is how we're looking at our impact today. Any other questions?
A question.
Yeah.
Around the circularity, and this is maybe my idea of understanding process, but plants pulling carbon.
Yep.
As they biodegrade, they release carbon.
Yep.
Is there a way to actually, through the biodegrading process or the microbes that are working on it, to have that carbon that could be released from the plant as it's biodegrading not be released?
Well, actually so there's some metrics are over the lifetime of the plant, it'll absorb more carbon than released during the biodegradation process. So there's a net win there, I guess, if you look at it. Because when you actually look at carbon, when you look at biodegradation, it's a combination of CO2 and water being produced, but a lot of that goes back into biomass or other byproducts that actually end back in the soil. That's why biodegradation is good for the soil, because it adds carbon and other nutrients back in. So biodegradation process will be looking at things like CO2 and water evolution, but also organic acids that can change the pH. Also urea and ammonia are produced during that process, and then more bacteria. More bacteria means more carbon in that soil. And then sometimes that bacteria will die. That's part of that CO2 evolution, but then most of that contained in that soil. So when you look at how nature works, the tree fell in the forest. My joke, you probably don't like it. No one heard it, right? You know, but anyways, okay. So the tree did fall in the forest. We saw it there laying there, and we came back 5 years ago, and most of it's decayed, but not all of it, right? There's a process. Nature built things to last, but it built things in a way where that tree falling adds back to the system, the ecosystem, and didn't do it away until the Industrial Revolution, where more carbon's being emitted into the environment. So that's kind of the approach that we look at. But we can recycle our materials. We can add product circularity into our process. It's not something we cannot do or won't do, but what we're trying to say is this is a process in terms of reducing your carbon footprint and knowing at the end of life this product will not create hazardous materials, leach out toxins in the environment, and will degrade over time. This is an interesting carbon footprint because it says 3.85, but we didn't include biogenics in this. And people don't understand, did you include biogenics? They don't really know what they're talking about. Biogenics is this idea that you should get a credit for when the plants absorb carbon over its lifetime and how much material is considered biogenic and stuff like that. So this is according to an ISO standard 14044 based on that. And that basically is a third-party validated LCA. We put this in the public domain to benchmark ourselves and allow you to benchmark us against your other technologies and the technologies you're using. So it's not sign a cloak and dagger, sign an NDA, you can't publish this stuff. This is who we are as a company, and more importantly, where we're going. So we have technology in the lab today that is sub 2, even close to 1 kilogram of CO2 equivalent. So this 12.8 is a conservative number. I've seen anywhere between 15 and 30 based on published data, and it's obviously whether you normalize it, average it out, or index it out, all these things that you talk about. But we're just trying to say is, well, don't worry about the brown line, worry about the 2 blue lines and benchmark us as we go through our innovation process and commercialization process.
It's an awesome technology, and thank you for going through this. Really appreciate it. The material that you, so your technology, plant-based, in your products, one of the signs outside said it's something like 70%, or I think in the slides it's up to 72%.
Yeah.
Is there also like virgin polyols that make up 100% of the product, or how does that?
So if you're looking at the polyurethane, standardized polyurethane material, you have 2 components. You have a isocyanate and you have a fully formulated polyol. So our fully formulated polyol is essentially 100% bio. The only two components that are not bio are the catalysts, which are not tin-based or heavy metal catalysts. We use more benign catalysts, and also the isocyanate. So you can look us up. We actually have a plant-based isocyanate patent that's published in the US. We're actually going through Europe, Canada, China, and some other jurisdictions to put this out there. And that patent is basically a plant-based isocyanate that is around 90% plant-based. It's highly functional, high performance. It can replace most MDIs out there, and what you do with it in terms of formulating that to make it a more functional or cross-linked product and doing all this stuff is, that's up for us to decide how we would, but we can take that pure MDI, use it in our material, and make a foam from it. And that foam is then going to be 90–95% plant-based, a much lower carbon footprint. But the idea behind that is, and I think kind of leading into your question is, what's the other material? Well, the other material is not good stuff, right? And that's why our carbon footprint today is 3.85. But how do we get to the other technologies working with? Well, we're not just looking at thermosets or foams. We have thermoplastics that have a higher bio content. We're also looking at, in our innovation pipeline, ISO-less polyurethanes. We have polyurethane dispersions that use a lot less isocyanate. And so we can really take this technology platform of using plants in a variety of different types of plants and chemistries and turning it into a variety of different materials that you can work with. So we also have patents around enhancing elastomeric performance on elastomers and stuff like that. Just not our space right now. We're kind of parking that stuff, but really what we're focusing on is, this is what we can do today. This is the 3 kilogram of CO2 equivalent. What we do tomorrow is really about working with the partners and adoption of the technology to expand it. Any other questions? You got a question, I can feel it. No? Okay, sorry.
Question for you. You talked about the input materials, being those waste starches and
Yep.
mass-grown corn. Does this technology work on extra waste from soybean production, or you got beets, or they had wheat this year, or what sort of input materials can be used to create this, or is it pretty specialized?
It's not specialized. We can look at different monomers coming from different feedstocks, whether it's starch or oil. So those are the two main, things that you would derive chemistry from. So plants make oils, they make starch, basically. Okay, so it doesn't matter where your starch comes from. So it can be, with other innovations and with partnerships that we're working on, those starches can come from second generation, third generation feedstocks in the future. But you have to start with something that is affordable, usable, ubiquitous, scalable today, and that's where you start with the industrial corn. And we don't have a war on agriculture here at Evoco. We kind of talked about the land use thing. We don't think it's a bad thing to work with starch from corn, but we also understand that these materials can be used in a variety of different regions across the world that may not grow corn. So what may be your feedstock there? How can you use that? And how can you adopt that and grow that? So the reason why plants are great is they're ubiquitous around the world. They're very regional, and you can use different things. Whether you use our technology or not, you can use someone's technology that may be made in Africa that may be using a similar platform or something like that can take these materials and derive them into something that's good for Africa or good for Asia or good for India, and I think that's what we can try to explain here, is that when you look at the impact towards net zero, plants have to be our future towards kind of really looking at less consumption, all these other things you can talk about. But if you really want to make an impact today and in the near term, you really have to look at plants as your source to replace oil. Go ahead. Oh, sorry, go ahead.
So do you own your own manufacturing and you're then selling final material products, or are you licensing your technology to manufacture?
Today we're fully vertically integrated, so we're working, we have our own production facility in Vietnam. We're looking to expand operations in the US. That's the start, but we're looking at partnerships in Europe, hopefully, maybe, you never know. But these types of things are really about not necessarily licensing, but today, for example, in China, we work out of Zhongshan. That's a partnership, so we distribute our materials there, but we don't work in the same standard way, which is you just buy our materials from a per kg perspective. We work as a partnership in the costing, and the brand kind of see it as a seamless thing of buying a finished good. But our Vietnam production and our Vietnam facility is really about taking that kind of 10 steps beyond, so we can actually introduce new innovations there, but more importantly, work on pricing mechanisms that may be more amenable to volume or to customers that need different pricing based on volume, right? Our friends just up the road from here. So, but I think where we kind of look at, vertical integration, we own the tech, we design the tech, we make our polymers, we make our systems, and then we produce a product from there.
Yeah, so obviously, like, you guys have the technology, but at the end of the day is, how do you get this message to the person that at the end has the shoe and has to decide, do I put it on the green can or the black can? So are you guys working with manufacturers to educate them on how they can relate that message to the end user to decide, hey, by the way, this is biodegradable. You can easily take it apart and put the parts that do biodegrade, and then the ones that are not, obviously, landfill.
Yeah, I think, our process today is working directly with the brands. So we take that presentation, probably a little bit more detailed one. We take it to the brands themselves, we go through it, they look at our LCA, they verify it in terms of their standards, we give them white papers and all that stuff, and they start to understand that. Now, they may not claim biodegradation because it doesn't have an ASTM standard attached to it, which again, I just like to say that's meant for food packaging, not for products that actually last, but let's not worry about certification right now, but they'll go out and make a claim that this is based on our net zero target, this is a credit from a sustainability perspective, but they're looking at it from a performance-based perspective as well. So this does perform, it's not just something that, it just slots in and gives you very little credit in terms of sustainability. This is a high credit on sustainability and a high performance product. Anything else? Oh, sorry.
I think you may have covered this, but I didn't get the whole thing. So the plant-based material, what is the plant and where are they, and where are they in the ground somewhere, or are they in a lab, or what is the source?
No, based on how many millions of pairs of shoes we made, they got to be outside of a lab. So, but I think what we'll say is.
So they're like trees that get.
No, it could be corn. It could be castor oil is a product we use a lot of as well, and it could be, and it's byproducts from food production. So we use some food waste, cellulose materials, but also lignin is a big technology that we're developing to. And lignin, if you don't know, it's a byproduct of paper making. If you look at a tree or a plant, it's made of 3 components, hemicellulose and cellulose. That's what you make, kind of cellulose is what you make paper from. But the lignin is the leftover. That's what protects the plant from the outside world, the nature and that sort of thing. So that lignin can't be used for anything. So we extract that or use it as a feedstock and derive new chemistry from that, or incorporate it directly into our materials and a variety of different things.
So there's never a plant that gets uprooted from the soil?
Well,
that's part of the.
Well, like if you look at corn,
Okay.
yeah, so you take the corn and the starch. There's a starch byproduct that that you take to make a monomer, and then we use that monomer in our process to make a polymer and then a foam. That's one application. Can I have a glass of wine now? Anyways, I'm over there if you have any other questions. Thank you very much. Appreciate it. Thank you.